Another approach to dimension reduction is called principal components analysis. The idea is to reduce the number of predictor variables. So we start with a bunch of variables, say 100 variables, and then we want to take the predictive power of those 100 variables and condense them into just a few, maybe 10 or 15 variables. If that's possible, then we should do that, and that's what principal components analysis attempts to do. So we're going to create new variables. The idea is we create new variables, and the new variables are a linear combination of the old variables. That is, you take each of the old variable values, multiply them with a coefficient and add them up, like in regression analysis, right? Regression analysis, we have b sub, no, we won't have the intercept here in principal component analysis. Throw the intercept out. So we have b sub 1 x sub 1 plus b sub 2 x sub 2, b sub 3 x sub 3, and so on. Add them all up, then you get one value for one principal component. Then you have a different set of coefficients and use those different set of b sub 1, b sub 2, b sub 3 and find the linear combination. You get the second principal component and so on. So here I'm going to we'll first illustrate with just two variables, and then we will do more variables in SAS. Okay. So here's the breakfast cereal example. So we have a bunch of variables here. We're going to take just two of them. Okay, calories and rating. Okay, so we have calories and rating. So two variables. Okay, and we can run a correlation analysis and then find that the variance in the diagonal values are variance. So calories has a variance of 379.63, rating has 197.32, and off diagonal is the covariance between the two variables. So off diagonal will be the same because covariance between calories and rating is the same as covariance between rating and calories, the same two variables. Okay, so we're going to omit the covariance. We're going to look at only the variance, and larger the variance in the predictor variable, the more powerful the predictive ability is, the predictive power is, because there are lots of different variations. So we will be able to use those variations in excess. See, the variation within a predictor variable is good. It is the correlation between two different variables that is bad. So we can convert this into percentages. So you add up the variances, right, and divide them into those. So you get 66% variance for calories and 34% variance for rating. So that's 100% of variance. So if the variance can be thought of as a kind of an indicator of the power of prediction among the variables. Now 66% of the power is with calories, 34% is with ratings. Okay, this is not perfect, but it is an indicator of the power that's available in the variables. Now, if we can generate another thing is, if you start with two variables, then when you do the principal component analysis, you'll end up with two principal components. Okay, the same number. If you start with 10 variables, you'll have 10 principal components. So with two variables, what we're trying to achieve is that come up with z sub 1 and z sub 2 instead of calories and rating. So each z1 value will be a combination of calories and rating. Okay, there is a little twist here. So we're going to take the calories and subtract the mean calories, and we take the rating and subtract mean calories, and then multiply by the coefficient for calories, coefficient for rating, add them up, you get z sub 1. And similarly, you have two different coefficients, and use those two different coefficients, and you get the for a given value of calories and rating, and you get a different z sub 2 value. Okay, so z sub 1 is a coefficient, and you take the difference between the value and the x bar. They're same for the second, add them up, so you get the value of z1, and two different coefficients for the second principal component. So you run, we're going to develop these in Excel. Okay, we'll see an example of how to develop these principal components. And we ran the two variables, right, calories and rating, in SAS, and we got the principal component coefficients here. So this is like first principal component, so that's our A, that's our B. So like A and B. The second principal component, that's our C, and that's the D. So like C and D. All right. Now, so Z sub 1 and Z sub 2 will be calculated in this fashion. So you go down the rows, first row, second row, third row. Each row, you compute Z sub 1 in this way. So that's A, that's B. And then you compute Z sub 2 using these two coefficients. And then if you calculate the variance and covariance of Z sub 1 and Z sub 2, and this is what you'll end up with. So you end up with 86% of the variance with Z1 and 13% or approximately with Z2. So instead of 66%, if between the two variables, if you keep correlation only and throw away rating, and you will be throwing away 34% of the predictive capability, right? Predictive power, approximately. Okay. But if you convert these calories and ratings into principal components, okay, and throw Z sub 2 out, okay, you'll only be throwing out about less than 14%. You will keep 86% of the predictive ability. So, so this is a way of converting from regular variables to principal components, and then throw away the ones with very low variance and keep only the high variance ones. So this is a way of reducing the number of variables or dimensionality. Okay, so here are some of the observations and the corresponding Z sub 1 and Z sub 2 values computed from the principal component scores. Now, another benefit of PCA is that unlike the original variables, principal components are completely uncorrelated. There is no covariance at all. See, for example, here we had the original variables, calories and rating. So these were the variances and these were the covariances, right? Now, if you do a variance covariance matrix for Z sub 1 and Z sub 2, you will find the variance of Z sub 1 and variance of Z sub 2 here and here, and you will have 0 for covariance. So which means the principal components have 0 multicollinearity, which is a good property. So that's another, suppose if you have a data set with very high multicollinearity, then it is a very good idea to convert the data set into principal components and then use the principal components now because they are not correlated. The multicollinearity has been eliminated. Now, generalization is, we did just two variables. Now, if you have a bunch of variables, okay, then again you do the same thing in SAS. You run the PCA, you'll generate the exact same number of principal components. So now you can set a target. Okay, you can say I want 90% of variance. Okay, suppose if 90% of the variance is accounted for in just 3 principal components, rest of them will be thrown out and you'll only keep 3 of them. So here is an example of 6. So you started out with a full data set, right? And then you generated principal components, and here is the proportion, cumulative proportion of the variance. So as you go down, you see when you hit two principal components, almost 93% of the variance is captured. And if you go down to that one, 8 components, you 99.99%. So here, with 4 principal components, you've captured 99% of the variance. So you can throw the rest of them out. Okay, one of the problems with principal component analysis is the variable's scale is different. Then the variables with larger values will have a higher impact on the variance of the principal components. So here, for example, this is the entire data set with of cereals data set. Okay, so these are the dummy variables generated for manufacture. These are the dummy variables for cold or hot, right? So you see most of the z values are very small, and suddenly there is this sodium with really very high values. So sodium is dominating all other variables in terms of finding the value of PCA. So that's because sodium in the original data set is measured in milligrams, whereas the rest of them were measured in smaller units, I think micrograms. So that's the reason why sodium is having too much of an influence, not because sodium somehow is a better variable, it's just because the way in which it is recorded, the scale in which the values are recorded. So in such cases, it is a good idea to use correlation matrix instead of covariance matrix in SAS, or you do normalization. Okay. If you do normalization, it'll work, but normalization in SAS, you can just choose between covariance and correlation. You don't have to normalize the variables because correlation means normalization will automatically take place. So here is PCA with using standardized variables. Okay. Then you see that it takes more principal components to cover 99%. For 99%, you need 15 of them. 90%, if you're satisfied with 90%, then 8 principal components are sufficient. So this is how PCA will work. You run the PCA. Okay. You can set a threshold value. Then SAS will automatically select only that many PCAs as necessary to capture your threshold value, or you can decide how many you want to have. So decide how many PCs you want to use, and then SAS will automatically use those PCAs in our predictive models.